Let's use the parametric equation in an example. So let's consider the line L1. So you'll notice that the line is represented by a scripted L subscript 1. Okay, so x is equal to 3 plus 2t, y is equal to negative 5 plus 4t. And so this is the parametric equation of line 1. A, we want to find the coordinates of the points on the line. B, we want to write a vector equation of the line. C, we want to write the scalar equation of the line. And then D, we want to determine if the line L1 is parallel to L2. Okay, so question 1, or number 2, I guess. A, we are asked to find the coordinates of 2 points on the line. So we can say t is equal to 0. Okay, would give us the point. Okay, so if we were to stuff 0 into here, we'd be left with 5 or 3 and negative 5. Okay, so that would be 1 point. Another point is when we say that t is equal to 1. So point 2 would be 3 plus 2 would be 5. And then here would be negative 1. Okay, so those are 2 points on the line. Okay, so B part. B asks us for the parametric equation, to find the vector equation of the line. So if we take this and we put it together, so x and y is equal to, okay, so 3 and 5 is our known coordinates of our known point, plus t, and then we just take the coefficients of t, so 2 and 4, which is then our direction vector. Okay, so that would be our vector equation. Let's move on to C. C part, okay, is we want to write a scalar equation of the line. Okay, so in this case, what we can do, let's go back to here. Okay, so let's take each of parts of the line in the parametric equation. In doing this and finding a scalar equations do not have parameters. So we're going to eliminate the parameters. So we can do that by having, well, since we have 2 equations, we're going to eliminate it by setting it equally to each other, okay, after we isolate for t. So first, let's write out each part. So 3 plus 2t, okay, I'm going to isolate for t. So x minus 3 is equal to 2t. T then is equal to x minus 3 all over 2. Okay, so over here, what I'll say then is the second part, y is equal to negative 5 plus 4t. Okay, now moving everything, y plus 5 divided by 4 is equal to t. Setting the t is equal to, or setting these equations equal to each other in order to eliminate t. So basically I'm substituting this t in for this t. Okay, so if it's another way of looking at it. Okay, so y plus 5 over 4. And now to make it look a little bit nicer in standard form, multiplying cross multiplication. So 3x minus 12 is equal to 2y plus 10. Okay, oops, 4. Right, so 4. Okay, rearranging, so 3x minus 2y. Okay, and then moving this over, so that would then give us minus 2 minus. Okay, and that works out to be 4x again. For some reason, I really want it to be a 3x, but made that a correction again. So here, what we could do is reduce this further by dividing everything by 2. So we're left with 2x minus y minus 11 is equal to 0. Okay, and that is our scalar equation. Okay. Okay, so in part D, we want to find out if L1 and L2 are parallel to each other. Okay, so how are we going to figure out if two things are parallel? Okay, two lines are parallel. So if we think back to grade 9, how did we do that? We looked at the slope. Okay, so if the slopes were the same, then two lines were parallel. In this case, in vector equations, what's similar to slope or somewhat equivalent would be our direction vectors. So if the direction vectors are scalar multiples of each other, okay, that means that the lines are parallel. So let's take a look at the direction vector. So here we have 2 and 4. Okay, I'm going to rewrite this. Okay, so in blue, what we have here is the vector for the direction vectors for each of the lines. Okay, so in line 1, it's 2 and 4. In line 2, it's 3 and 12. Now, are they scalar multiples of each other? And that means both coordinates. Okay, so is there a number that we can divide both by to get the other? In this case, no. So we can conclude that the two lines are not parallel. Let's consider the next example. So consider the line with the scalar equation 4x plus 5y plus 20 is equal to 0. We want to graph the line, and then we want to determine a position vector that is perpendicular to the line. Okay. After that, we want to write a vector equation of the line. Okay, so when you're looking to graph or you're interested in graphing a scalar equation in standard form, the method that I always use is by finding the intercepts, because I think it'd be the easiest. Okay, so here's our scalar equation. If we want to find the intercepts, we want to find our y-intercept. Our x-intercept. Then we can cross off. What I do is I cross off the term that has y, and then I rewrite what's left. Okay, so I say 4x. I'm going to move the 20 over, is equal to negative 20. Okay, x then is equal to, too many equal signs, negative 5. Okay, when I want to find my y-intercept, x is equal to 0, so then I go back to here and I cross off the term that has x, and I rewrite what's left. Y is equal to, moving the 20 over, negative 20, y then is equal to negative 4. Okay, so we can easily plot this on the graph. So I'm going to go back to the graph here. So what we can do now is simply use those intercepts. Okay, so we have the x-intercept is negative 5. Okay, so the y-intercept is negative 4. Okay. So there's our graph of our line. Okay. Now we want to determine a position vector that is perpendicular to the line. Okay, so the first thing that we can do, if we're thinking back to grade 9, if we had two lines that were perpendicular, okay, their slopes were negative reciprocals. So the first thing that we should do is find a direction vector of the line, and then we can find the position vector that is perpendicular to it. Okay, so let's find the direction vector. Okay, so we can simply say that the direction vector, okay, so if we said that those 2 points, this is A and this is B, if we said here, if I said that this was A and this is B, right, then we're going to say that OB minus OA will be our direction vector. So that just leaves us with 5 and negative 4. Okay. Okay, so I want to find some generic vector we'll call D, that is x and y. Okay, that is perpendicular to M. So I'm just going to say 5 and negative 4, okay, times x and y. Okay, remember that the dot product, when they're perpendicular, is equal to 0. Okay, so that's what I'm doing here. I'm using the dot product property. So here we will then get 5x minus 4y is equal to 0. Okay, so then I'm going to isolate for y. We'll say 5x is equal to 4y. y then is equal to 5x over 4. Okay, and so we can choose a value of x now. Okay, to make it easy, why don't we choose 4, so then the 4's will cancel out. I'm going to say x is 4. That means that y will then be equal to, excuse me, 5. Okay, so that means our direction vector, or sorry, our position vector that is perpendicular to our line is then 4 and 5. Okay, and so the key here is this property where the dot product of two vectors that are perpendicular is equal to 0. Okay, and we can use that dot product. Okay. Okay, so let's move on to part C. Okay, so in this part, we want to write a vector equation for our line. Okay, so that will be x and y, and I'm just going to write it in components here, or vector form. So we said was, so one of our known points, we'll use one of the intercepts. We'll use the x-intercept, so it would be not minus 5 and 0, plus remember the parameter t, and then our direction vector that we came up with, which is 5 and negative 4. Okay? And remember that t belongs to the set of real numbers. Okay, and so that completes that example. I just want to introduce to you a concept called the normal vector. Okay, so a normal vector of a line L1, we'll say, which we denote as being n, the vector n, okay, is perpendicular to our line of interest. So if we had a line ax plus by plus c is equal to 0, then our normal vector, okay, the coordinates x and y, are simply the coefficients of the variable. Okay, so the coefficients of x and the coefficient of y, that correlates to the coordinate of the normal vector. One last thing I want to talk about is equations of lines in 3-space, or R3. So we treat them the same as we would in 2-space. However, we have an extra parameter, which is z. Okay, so here we have the vector equation for a line in 3-space, or an R3, and then a parametric equation in R3. So we still only have one parameter now, we just have a third coordinate, z. And that concludes our lesson for today, and we'll see you next time.